All right, the next question on the chopping block is, one particle of charge Q1 is held at rest at the origin. Another particle of Q2 approaches along the x-axis in hyperbolic motion. We've seen that before. It reaches the closest point B at time t equals 0 and returns out to infinity. A. What is the force F2 on a Q2 due to Q1 at time t? B. What total impulse is delivered to Q2 by Q1? C. What is the force F1 on Q1 due to Q2 at time t? And what is the total impulse delivered to Q1 by Q2? So we kind of have a reflective question here. But, if we were to try to graph this out here soon, we'll see exactly what that looks like. But, let's dive into part A. Since Q1 is at rest, we can use Coulomb's law for it. So F2 equal Q1 E1. So the reason why is because E1 stays constant there. So we're good to go. Q1 is at rest, so E1 is stationary. So we can find a static field, no problem there. All right, so we get that as our field. The impulse is just the integral of F2. Push out the constants. With this particular integrand, this looks like the arc tangent. So that's what we find. And we see that arctan infinity and negative infinity, that just gives us plus or minus pi over 2. If you remember your inverse range there that we have. So A and B really aren't too bad, I don't suspect. It's C and D that are going to be a little more troublesome, so we got to be careful. That being said, you see F2 is equal to this, and I2 is equal to Q1, Q2 over 4 pi epsilon naught, pi over BC. Again, B is the closest approach. C is the speed of light, so we're good to go there. And now for part C, we saw earlier that a particle Q2 moving along the x-axis had an electric field of the form E2 equal negative Q2, 4 pi epsilon naught, 1 over r squared, C minus V over C plus V in the x-hat direction. In fact, I think that was 10.20. Yeah, I think that was 10.20. I'll link it in the question below so that you can reference it. But it was a pretty easy approximation. Nonetheless, our script r squared has to go to x to evaluate it at the retarded time. And then v is x prime evaluated at the retarded time. So we're going to have to do some work here. Here we need to evaluate x and v at the retarded time, tr, which is given by c times t minus tr is equal to absolute value r minus wtr, which we just said equal to x of tr. So we know what that is. That we've seen this before with the square root. Set everything open, distribute as much as you can, cancel what you can, solve everything for tr. Here we get tr is equal to c squared t squared minus b squared over 2c squared t. Note, as we found in problem 10.7, Q2 comes into view for Q1 at time t equals 0. Before that, it can exert no force on Q1. So there is no retarded time, okay? Because it's only at t0, so we can't divide by 0, so be aware of that. And from the graph of tr versus t, we see that tr ranges all the way from negative infinity to infinity, while t is only from greater than 0. So let's go look at that. Okay, so we have t, which just in the vertical. The horizontal axis is t. Tr is equal to the vertical axis. And we see that if we graph tr as a function of t, it has that hyperbolic kind of motion again. And we see that it only goes as close to tr and t, which is the length b at t equals 0. Okay, that's as close as it gets, but clearly t can only exist from 0 to infinity. Meanwhile, the retarded time gives us something before and after, so we're going to have to be slightly careful with that particular observation point. So with that, let's go back and reformulate how we're going to approach this with the position and the velocity. So the position at the retarded time is equal to ct minus tr, and that's equal to c. So let's formulate that based on finding a common denominator, and that's why we color coded it red. And we see cancellations, of course. Cancel, cancel, cancel. The derivative of this goes to 1/2, put the negative in the numerator or numerator of the power. The 2 cancels with the 1/2, and we're left with c squared t over b squared plus ct squared. So what this actually tells us is that the velocity is equal to c squared t over the position at time t. Pretty cool. So that being said, we have now we just evaluate at the retarded time. And with that, we plug in TR. Cool enough. Cancel, cancel all the way through, whatever is possible. No biggie. We found XTR and we found TR, so whatever we can do to simplify, I think we got it in the bag. That being said, our electric field 2 for this moving charge is horrendously nasty, okay? So we get the 1 over X at TR, and then that's squared, and then the bracket for C minus V, and then C plus V. So, if you can cancel down or simplify this however you deem necessary, please do. We factor a C out and try to tame that down, cancel it in both the numerator and denominator. We divide by a fraction, so we multiply by the reciprocal, which is where we get 2c t squared in the numerator, and then c squared t squared plus b squared all squared. And now we have 1 minus, and then we have 1 plus. And as you see, I color coded it blue and purple because we have to find a common denominator. Those common denominators make a lot of work for us, so we're going to go ahead and cancel out everything that we possibly can. In the finding of the common denominator, we see that the denominators in the numerator and denominator actually cancel. Wonderful. And then we see the CT squared cancel, the B squareds cancel in the denominator. So we can tidy up pretty quickly, I would actually say. We see that the 2c squared, t squared, and that reformulated denominator cancels with the 2 for the b squared and the c squared, t squared from the numerator, from the 1 over x evaluated at tr, whatever. You see all the algebra there. Let it simplify down. And after all of that, what we see is that force is equal to Q1E2 is equal to negative Q1Q2 over 4 pi epsilon naught 4b squared c squared t squared plus b squared, all squared in the x direction for t greater than 0. And of course, if t is less than 0, then f is 0. Okay, cool. That being said, whenever we go to find the impulse of f of 1, instead of going from negative infinity to infinity, we have to go from 0 to infinity. So that changes things a little bit. And what we see is that, again, we get some, the inverse tangent again. I'll let you sift through the calculus of that and how to set that up, splitting up the integral, all that kind of stuff. All the fun stuff to get rid of things. Integration by parts. Gross stuff. Sift through the calculus on your own. You see that we get some that pi over 2 from the inverse tangent again and simplify things down. But notice here that I1 is equal to negative Q1 Q2 over 4 pi epsilon naught pi BC, which is equal to negative I2. So the impulse is equal and opposite here. But it's an interesting cross production here that we see. And I'll have some more notes for you in the description, but have fun with that calculus. The retarded time comes back to bite us again.